Thank you. Okay, so today we're welcoming Sarah Lee to talk about improved synthesis of Toffoli-Hadamard circuits. Please take it away.
Thank you very much. And I'm very grateful to have this opportunity to share our work. I first want to give a shout out to Matt, Andrew, and Julian. So we work on this collectively. And this is also work based upon their 2021 submission to 2020 submission to QPL, the number theoretic characterization of the restricted Clifford+T circuits. So we're looking forward to hearing all of your perspectives and to hopefully better our work. So let's get started. Well, before we talk about this technical details, I want to first motivate the circuit synthesis problem, or more generally, the quantum circuit compilation, because for most people working semantics or programming languages, it may be a bit strange, like why we're thinking about decomposing unitaries. Well, the reason is quantum algorithms can carry out much more powerful computational tasks than some classical algorithms. And like finding a quantum algorithm itself is very hard. But more generally, if you have a quantum algorithm, you want to translate it from a human understanding language to something that quantum computer can understand, which correspond to a sequence of elementary gates. And then finally, once we have this design in terms of the building blocks, the quantum engineers in different companies needs to map it to the physical architectures that they are working with. However, the quantum system is always very noisy, and our physical qubits are incredibly sensitive to noises. So although we have quantum error correction and fault-tolerant protocols that can help us better the computational accuracy, but if the computation itself takes too long to execute, then our qubits will just decohere while waiting for the computation to end. Or, for example, our gates are usually having this poor fidelity such that every another gate you add on top of your computation, it will introduce some additional error. Then at the end, your computational results will not be accountable. So we are trying to meet the quantum error correction experts from the other end of the story. Like we're trying to define an algorithm that gives us a shorter circuit as much as possible. Well, by shorter here, we mean a circuit of lower complexity in terms of the gate count. And I forgot to mention earlier that feel free to stop me if you have any questions. All right, so we are going to talk about two restricted Clifford+T circuits. One is what everybody has known about, the Toffoli-Hadamard circuits. It is arguably the simplest approximate universal gate set for quantum computing. And it is well suited for many purposes, such as quantum error correction, fault tolerance, and quantum Fourier transform. Moreover, many people in our community, I mean Zach's community, have studied it. For example, Miriam, Alex, John, Huinol, I apologize if I pronounce your name wrong, have been studying on this ZH calculus, which is a diagrammatic calculi to work with a very similar algebraic structure. And we also have Huinol's last year's paper in 2020, well, this year's paper in 2023, working on the path sums, and people back in 2013 have studied the quantum logic. So it is a very well-studied gate set, so we think, it may be interesting for us to derive some interesting results. And beyond that, we're going to introduce you to another circuit. It is of a very similar mathematical structure to the Toffoli-Hadamard, but instead of having just one Hadamard, we have two folds of Hadamard. It's denoted in this shorthand notation, K. And I'll introduce this in more details in the matrix form. But basically, today we're going to work with these two kinds of circuit hand by hand. And I also want to note that the reason that you're seeing here, not just the Toffoli and Hadamard, is because in the classical reversible computation, Toffoli can generate the single qubit NOT gate, two qubit CNOT gate with the help of ancillary bit being assigned to 0 or 1. So that's why when we're talking about Toffoli-Hadamard circuit, we refer to circuits over NOT, CNOT, Toffoli, and Hadamard circuit, Hadamard gate set. All right, so the basic gates that we're going to use today are the scalar, which is a 1-by-1 matrix, and we have a Hadamard, and K is just a tensor of Hadamard. And you may have noticed that Hadamard has a scalar of 1/√2, and K has a scalar of 1/√, right? 1/2. So you can see K is somehow kind of like belongs to this framework described by Hadamard because root 2 can always be written by a square of like a square of root 2. And we also have not, C naught, and Toffoli gate. All right, so over the past decade, researchers such as Peter Selinger, Julian Ross has developed this number theoretic correspondence between the circuits and the matrix groups. Now, this is very interesting to study because instead of looking at this block notation in time slices, we're able to study the mathematical structure of the quantum circuit. And this may reveal interesting properties that we could leverage to design better, interesting algorithms for circuit synthesis. Therefore, now, instead of studying the quantum circuits, we can study the matrix groups. The first matrix groups that we're going to look at today is called the orthogonal scaled dyadic matrices. Now, why this is named that way? Because we think of a unitary whose elements is real as an orthogonal matrix. This means that every pairs of rows or columns are orthonormal. And we also define the entry of this matrix to be of a very specific type. So if you write out this element in this group Ln, you can think of it as every element is composed of an integral matrix M with a scalar, and this scalar is 1 over root 2 to the power of k, and k is a non-negative integer. As an example, if we're looking at a 4x4 matrix, then you can think of this 1 over root 2 as a scalar. And later on, we can drop the scale and then say, well, what if we define an orthogonal dyadic matrix? Then these matrices are also unitary, and they're just a real version of it. And they're also over a very interesting ring that is called dyadic fractions. So every element in this ring can be thought of as a numerator that is an integer and the denominator, which is a power of 2. And we also have a group of orthogonal dyadic matrices where you can just factor out 1 over root 2, to some power from every component, such that this element of the group can be represented in this form where n is an integral matrix and come with a scalar. And later on, we'll talk about this k, and it will have a very interesting characteristics, and that will help us to design our exact synthesis algorithm. As an example, let's look at a 5x5 matrix. And as you can see, if we factor out 1 over 2 to the power of something from every component, then you can get an integral matrix with a scalar. And there are some kind of correspondence or relations between the ON and LN, and they're described as this subgroup relation. So if you look at this 4x4 matrix, you'll see that we can actually transform the one on the right-hand side as a power of root 2. Then this is actually an element in L4. So this tells us that the orthogonal dyadic matrices and the orthogonal scale dyadic matrices, they basically just differ by a scalar 1 over root 2. And this is very important because today we're going to present 2 algorithms. One is a householder decomposition, and the other is a global synthesis algorithm. So both algorithms works with both groups, but in one case, our algorithm works much easier with the Ln, and in another case, it works with On. Now, because these 2 groups are kind of very similar, just up to a scalar, so in what follows, I'll use or work with these 2 groups interchangeably. Okay, so before moving on, do we have any questions? Let me see. We're all good?
Oh, Sarah.
Yeah.
You go back to this previous matrices. I'm not like, are these supposed to be the same matrices somehow? I didn't quite catch that.
Oh, right. So, so the left-hand side matrix is a different matrix from the right-hand side, because if you view it as an element from L4, they have different least denominator exponent. And I'll explain later what is LD, but there are 2 different matrices.
Oh, okay. So yeah, they're not supposed to be like the same unitary up to a Hadamard or something like that. They're just arbitrary examples here.
Oh, that's a good point. Actually, I think maybe we can apply I tensor Hadamard on this gate and see if we could reduce it to the left-hand side.
All right. Yeah. Right.
Right. So the idea is the right-hand side is its own matrix. Thanks for the question. Okay. So in our framework, we define a constructive membership problem. basically that is a mathematical framework that will reason with the exact synthesis algorithm. So let's say G is a group and S is a set of generators of G. Then if we take let's say an element that we want to decompose it over this generating gate set, then basically we just perform this sequence of S1 to SL, which are just the generators, such that they together compose the element that we want to decompose. So this is almost like this reverse engineering idea. It's like you want to find the composition or decomposition of something and just you reduce it, and then you just then you reverse the process. Now this dot product here corresponds to the group operation, but if you look at it from a semantic perspective, this is a matrix multiplication. And then the L here just denote the length of the word. By word I meant the sequence. So if you have a smaller L, the shorter the sequence you'll get, which correspond to a smaller quantum gate, a quantum circuit, and then this will give you a better solution. Now, when the solution is optimal, it will give you like a optimal quantum circuit. So we, in quantum circuit compilation, we kind of call this procedure or this algorithm to solve CMP as the exact synthesis algorithm. All right, so this is a work that has already been done, but it's very important to lay the foundation. So I'm just going to quickly go through it. And for some other small parts, I'll have to ask you to trust me on some of the technical details because we'll not have time to go through all of them step by step. So the idea is there is a direct correspondence between the circuit that we're looking at, which is the Toffoli-Hadamard circuits or the Toffoli-K circuits, with a unitary matrix group that we just introduced, which is the orthogonal scale dyadic matrices, which is Ln, and the orthogonal dyadic matrices, which is On. And the gate complexity given by the AGR algorithm in the 2020 paper is actually 2 to the power of n log n k. This is not really good, right? Because n here is actually a dimension of the matrix, but we know that in unitary, our dimension is actually 2 to the power of n, where n is the number of qubits in our system. So it's really not good. So we want to improve it. Well, so this motivates the work today that we're trying to find a better solution. And in a kind of like a bird's eye view, we reduce the complexity from exponentially large to polynomial large. And then further on, later on, we introduced this global synthesis network to reduce it to linear in K when we were working with the small size quantum circuits. So I'll tell you more about it. But first, let's define some n level operators that is used in the exact synthesis. The first one is a 2-level operator. Well, think of it this way. If you have a 2x2 matrix, okay, it's a unitary and it's composed of 4 elements, and you want to define an extension of it such that now this U alpha beta can work on a larger matrix, but it will act locally still as U. So how do we do that? Well, this describes what I just said. So you can just embed this U into an identity and then keep all the other elements, on the diagonal as 1. So for example, if you have an X gate and then X to 3, meaning that you want to have your X, your NOT gate act non-trivially on the second and the third element in the vector, then you just plug it into this matrix, and then you can just basically just perform the swap on V2 and V3, and you'll get this vectors. Now you can also generalize this notion to a 4-level operator by starting with a 4x4 matrix U and then embed it into a larger identity matrix such that you just put this part into the corresponding 1, 2, 4, 6 column and 1, 2, 4, 6 rows, and then you'll have this enlarged matrix still unitary and acting on a 6-element vectors. Now this 4-level operator will act locally on V1, V2, V4, V6 to perform this linear transformation defined by K, and it will act trivially on V3 and V5. So using this notion, we define a new generating set, Fn and Gn, so that Fn has 1-level operator, 2-level operator, and a 4-level operator, along with I tensor H, and then G just has this 3-level operators. So in what follows, I'm going to drop this n over 2 because it will be very clear from context. But the reason we're trying to introduce this Fn and Gn is because they provide a handy notion for us to work directly with the columns in the matrix. It's much more intuitive than working with this, tensor of Hadamard or tensor of K-gate. And we also kind of learned from the past literature dated since 1995 that this generators can actually be exactly represented by the two gate set that we just discussed about using O log n operators, as you can see here. Now, with this notion in mind, we're able to kind of rephrase the correspondence that we just mentioned. That is, if you have an n by n matrix, U, and U is in this group Ln or On, then it corresponds exactly to elements from Fn and Gn through the matrix composition, which is the matrix multiplication. So do we have any questions now, or can I proceed?
So just to be clear, M is the number of qubits?
N or M?
So if you have N and M, and then M is the number of qubits and N is the size of the matrix?
Yes.
Okay, so when you say to take a log n operations, you're saying it takes like linear count in the number of qubits, right?
Yes.
Yeah. Okay.
Okay, thank you for the question. Now let's proceed with the notion of LDE. So LDE intuitively give us a metric to gauge the distance of our unitary to the identity that we want to reach. By this, we mean, let's say if you look at a column vector, okay, it's over dyadic fraction, then you could just factor out this 1 over 2 to the power of something. But this is not a reduced vectors, right? Because you can still continue to factor 2 from every component. Now, if you factor out 2, and then you can just reduce it from both the numerator and denominator, and you'll get this. And at this point, you're no longer able to factor out 2 from the component of these vectors, so you'll have the least denominator exponent for this vector. Now, this is almost like saying, oh, this is the simplest form that we can reduce our vector to. Now, in our circuit synthesis, we're going to use this notion to gauge how far we are from the basis vector. Now, this notion can also work with a matrix, analogously. In the synthesis, there are like some very elementary steps. The idea is it is actually a Gaussian elimination. You start with the rightmost unfixed column, and then you just reduce it to the basis vector. Okay, and this one is set, and then you move leftward, and then you work on the next unfixed column. Then at every step, your problem is reduced to synthesize one column. So this is why we're kind of looking at this base case, parity count and parity reduction. So the base case says, if you have a unit vector and its LD is equal to 0, then it is a basis vector up to the sign. Now, we don't really mind where this 1 is in the vector because you can always use the 2-level NOT gate to kind of swap them. And you can also have a count lemma saying that if you have a unit vector and its LDE is not equal to 0, then the number of odd entries in its integral part, in its reduced form, must be a multiple of 4. And finally, if you always have 4 odd entries in a vector, there is a deterministic way to assign the 1-level and 4-level operators to act on this vector such that it will be reduced to a vector with a smaller LDE. Or on the others, in other words, you will reduce the odd entries to even entries. And why this is important, we'll see this later. Okay, so let's suppose we have an 8-element vector, and it is of LDE equal to 2. Now, by assigning these operators, you're able to act locally on the first 4 elements such that the top 4 elements now become even. But this is not done because we still cannot yet factor out 2 from every component. We still have 4 elements happening here. Then we apply another sequence of generators such that now we have a sequence of, well, we have 4 even entries in this new vector, and we can factor out 2 from them, and then we'll get a reduced LDE, which is 1. Now, reasoning analogously, another sequence, and we'll get to the last one. So basically, the previous parity lemma ensure that the odd entry always occur in quadruple, and the parity reduction lemma ensure that we are always capable of sending odd entries into even entries. And combine this together, we have our column reduction. Now, the AGR algorithm, as we mentioned earlier, it is a variation of Gaussian elimination. It dated back to 2014 when Zhao Salinger proposed the exact synthesis algorithm. So this is exactly the same form. We start from the rightmost column, reduce it to the identity, and then we start from the second rightmost column, reduce it to the identity. At every step of the reduction, our algorithm output a sequence of generators over the generating set that we just mentioned. And then we can just concatenate these words at GL all the way to G1. This means that this sequence of generators will send the input M into the identity. Now, because we know that our generators are unitary and they're self-inverse, then by taking the inverse of this word, you can just flip them, and then you can just take the result, which is the decomposition. So as you may have seen, throughout this reduction process, we're using the LDE to gauge how far we are from either the basis vector or the identity matrix. So this is the reason we think LDE is a very important parameter for our unitary matrices.
Sarah, could you go back 2 slides?
Yeah.
One more? Yeah. You say you always have a multiple of 4 odd elements?
Yes. So no, quadruple of odd entries.
But you could have the vector 1, 1, and then all zeros, and then with a denominator exponent of 1, right? Well, why is it not possible?
Oh, that's a very good question. So I'll actually mention this in a later technical lemma. May we wait till then? Because then I'll show you a proof for this.
Okay, but so you're not dealing with arbitrary unit vectors, but some special type of unit vectors that come from the unitary, and that's what gives this restriction? Or, because you can write down a unit vector which has 1, 1, all zeros, right?
Right. Yeah. So we're dealing with a column vector retrieved from orthogonal dyadic matrices from the group that we just defined. So every vector you see here is actually a column vector from ONZ1/2. So it is of unit norm, and it is also orthogonal to all the other column vectors in an orthogonal dyadic matrix. So, well,
oh yeah, sorry, yeah, I see my mistake, I think, because you're taking the inner product, so then you square the LDE. Yes. That's why you have this. Yeah, okay, yeah, cool.
Yeah, okay. Right. So the complexity is analyzed before, but I just want to demonstrate why it is so expensive to do this AGR algorithm kind of column by column. Now, we know from the earlier slides, the unitary reduction is reduced to the column reduction. Now, when we look at the column, in the worst case, we have n entries to deal with, then the number of generators in Gn is O and K, and K is the least denominator exponent of that column. But note that here, we are not dealing with every column independently, right? So when we are applying our M-level operators, yes, indeed, they're acting locally on those entries, but they may have also affected the other columns. This means they may mistakenly make the other columns much harder to synthesize. By this, I mean they may get higher LDE. So this is captured by this recursive, or it's not recursive, but it's just like this cost analysis. You could see that, if you're starting with first column, the cost is O and K, but if you go to the next column, the LDE will be increased at least by 1, but because it's 2 to the power of something, right? So you're actually adding 2 to the cost function. Now, just analyzing this from the first column to the last column, you'll actually have this exponential size, and by summing them up, you'll get 2 to the power of nk. So this tells us that in order to reduce the complexity of the AGR algorithm, we may want to think a smarter way to do the synthesis globally instead of looking at every column step by step. So there are two ways to do it. Oh, before moving on, do we have any other questions about the previous part up to this point? Okay, so let's talk about the householder algorithm. So this is adapted by Kliuchnikov's work in 2013. So the idea is we don't just synthesize the unitary that we are interested in, but instead we go to a higher dimensional Hilbert space, and we simulate U using U prime with an ancillary qubit being assigned to minus state, cat minus, and then we can write this U prime as a product of reflection operator. Then this reflection operator has the count of them is n. But this reflection operator is much, much easier to synthesize as follows. So we define a reflection operator around the unit vector by just taking the I minus 2, this outer product. And then this is a very technical lemma proposition, and I have to ask you to trust me on this. But basically, when you have defined such construction, you no longer have to synthesize the entire matrix to get ARP psi, but instead you only need to synthesize the first column in ARP psi. And recall earlier we just analyzed the column reduction lemma give us an ONK of the cost, right? So we just kind of take advantage of such construction and get this complexity to synthesize a specially defined reflection operator over a unit vector. Now let's come to the unitary simulation and see how we define it. Firstly, we think of U as an element in the orthogonal scaled dyadic matrix group. It's 1/√2 to the power of k with an integral matrix. And then U can be simulated using U prime as defined here. And then we are also defining this U prime to be a product of the reflection operator around this unit vectors. And this unit vector has very interesting properties, and we'll talk about this soon. Now, this can be diagrammatically described as follows. U is acting on n qubit. Now, U prime is acting on n plus 1 qubit because this ancillary qubit is assigned to minus. Now, when you input a psi into this U prime, you could just, try it with this definition. You will get exactly the U psi as an output with the change or like the flip eigenstates from minus to plus by construction. So we could actually verify two things about omega j. It's very interesting. Firstly, omega j I is a unit vector, and they are orthogonal to each other when j is changing from 1 to n. Now, you can also define omega j plus just by changing this minus to plus. And then these vectors are also unit and also orthogonal to each other. Moreover, omega j plus and omega j minus are orthogonal to each other, are pairwise orthogonal as well. Now, what does this tell us is omega j and omega j minus and omega j plus form an orthonormal basis for our Hilbert for our space. And by the completeness relations, we know that we can just calculate the sum of outer product of the orthonormal basis, and this will give us identity. Moreover, one can verify that omega j plus is corresponding to the +1 eigenspace of U prime. Omega j minus correspond to the -1 eigenstate. Omega j minus is the -1 eigenstate of U prime. Therefore, by the spectral theorem, you can write it in this way, where this minus just comes from the eigenvalue. So combining these two equations, you can just take I minus U prime and it will give you this. But note, if you just move I to the other side of the equation, you will actually see this is exactly what we just talked about, the reflection operator. Note that here I'm taking a small jump from summation to a product. This is just because omega j's, we just mentioned they are mutually orthogonal. You're leveraging this to derive a simpler notation. So basically, we prove that if you have a unitary, you can just define a U prime of one qubit larger than U. that exactly simulate U under the presence of an ancillary qubit. And then this U prime has a nice construction as follows. So based upon this construction, we can show that using the householder decomposition, we can exactly synthesize this unitary element in Ln using On squared k elements, because U prime is composed of n reflection operator, and every reflection operator take On k generators to synthesize. So n of them will take On squared k, right? And basically this completes the proof. Do we have any questions about?
Yeah, Sarah, can you say in what way does U prime simulate U? Like, what does that mean?
Yes, so I mean that with the participation of an ancillary qubit being assigned to the minus state, U prime act on a minus tensor psi as a plus tensor U psi. So it's basically just this diagram here. By simulate,
right, so you prepare an ancilla in minus, and then you apply U prime, and then you measure the ancilla, which you will always get a plus, and then you've formed U on the other qubits.
Yes.
I see. Yeah.
Well, thanks for the comments. I did not mention it, but that's very helpful. Yeah. Any other questions? Okay. So let's recap. The AGR algorithm carries out the matrix factorization locally. So it's synthesized one column at a time. When n is fixed, you could see that actually, I did not show it here, but let me see. Well, actually, this is a good example. Now, this is a complexity for the householder decomposition, right? Now, if you fix n, you'll see that this notion will be reduced to something linear in K. This is really kind of trivial, right? But it is not trivial from the sense of quantum circuit compilation. And I will show you this very soon. But this observation is what motivates us to devise the global synthesis, because we believe that when we don't look at any dimension, but instead looking at some fixed dimension, we may be able to derive a dictionary to guide us to do the global synthesis of the entire matrix instead of doing it one column at a time. And throughout this process, we're leveraging the number theoretic perspectives, of these two groups, Ln and On. This is not the first time that people have done this. So back, I think about almost a decade ago, Peter has this undergraduate student, and he carried out this global synthesis from other group. And there's a PhD student also had this thesis on it. So we kind of just we work out this independently, but I'm just saying that people have already looked at this like many years ago. And there's also a group of people in Germany. They have worked on this global synthesis approach, but they did not use the number theoretic study. They use this tree pruning method. We checked out their paper when we were doing this project, but we decided not to pursue this direction. So for today's talk, you'll look at mainly just a number theoretic perspective to deal with a global synthesis algorithm for the Toffoli-Hadamard circuits. Okay, so we are going to define the method for the L8, which is a 3-qubit Toffoli-Hadamard circuits. You can also work with 2-qubit, 1-qubit, and then we're going to leverage this to work with On, which is a Toffoli K-gate. All right, so the intuition is, if you look at your matrix, and then you can just derive the you can derive the LDE of the matrix as K. Now, if we can find a G1 that is a sequence of generators guided by our dictionary for the synthesis, then we can reduce the global LDE strictly by 1. Now, after reducing everything to all K to 0, then we will get an identity. It's just an analog of the basis vector lemma we just mentioned, and then we complete the process. And by taking the inverse, we have the decomposition. But before that, we need to define a few notions. Firstly, it's called the binary pattern. It means if you're looking at the scaled orthogonal scaled dyadic matrix and factor out this 1/√2 to the power of the LDE, then you'll have an integral matrix, but we're not done there. We look at their modulo 2. Basically, we're just looking at the parities, whether it's even or odd. If it's even, it's 0. If it's odd, it's 1. So as an example, if you have an element that is from L5, and then you look at this integral part, and then you just map all the odd entries to 1 and even entries to 0, and you'll get this. And we'll later show that for L8, L4, and L2, the binary patterns are finite. In fact, it's actually only a few number of them compared to infinitely many elements in these groups. All right, so the first property is the weight lemma, and this is actually the one that I promised I'm going to tell you about, is that if you have column that is taken out from the orthogonal scaled dyadic matrix, and you take its binary pattern, then the number of ones in this column must occur in quadruple. And as John pointed out, basically you're just taking the inner product of these column vectors, and now you just have the sum of the square of every integer component is equal to 2 to the power of k. Now here we're restricting our k to be larger than or equal to 2. This means that the sum is equal to 0 mod 4, right? But recalling number theory, if you square an even number, you'll get 1 mod, if you square an even number, you'll get 0 mod 4. If you square an odd number, you'll get 1 mod 4. So in order for the sum of the square of this, this components being congruent to 0 mod 4, this ones must occur in quadruple. Otherwise, you cannot have the sum congruent to 0 mod 4. Therefore, we conclude that the odd entries in the column vector of a unitary element is a multiple of 4. Any questions? Okay, I guess maybe she just turned on her mic. All right, so another property is that if you have two columns from the binary pattern of this U, then the ones in this two column must collide evenly many times. What do I mean is this? For example, this is an evenly collision example. U1 and U2, there are two binary vectors, and you see that 1, 1, right? They kind of, the third row and the second row collide. Now, if you look at this guy, U3 and U4, they collide oddly many times because there are three positions that are identical. Now, by leveraging these two lemmas, one is the weight lemma and the other is the collision lemma, we're able to find 14 binary patterns such that you, oh, by the way, Ariane, I think your mic is on. Oh, okay, good, right. So we could find the 14 binary patterns up to the row and column permutations, meaning that, even if you didn't find the exact one that we demonstrate, it is just a matter of shuffling the rows or columns. If you are interested in the case distinction, I can show you our paper, but let's for now just focus on study the properties of these patterns. So from A to K, there are 11 of them, and these guys are nice. And then from L to N, there are 3 of them. These guys are not nice. What do I mean is as follows. If you look at the nice binary patterns, they actually follow the idea that the identical rows occurs in even numbers, right? You can have 4 identical rows or like 4 identical columns. But if you look at an unnice one, you will have oddly many identical rows or columns in these 3 cases. So this is characterized by the definition. Here, if we said something is row paired and this something is a unitary binary pattern, then it means that identical rows occur evenly many times. And on the other hand, if it is column paired, then identical columns occur evenly many times. And then, for example, if you look at a 4x4 matrix, then these 2 rows are identical or these 2 columns are identical. But if you look at the right-hand side, the V bar, then identical columns are paired, but identical rows occur oddly many times. So this guy is not nice. Now, why do we need this? Because we discovered that when the binary pattern is nice, there is a very convenient way to apply the I-tensor Hadamard gate on the left-hand side of the U or on the right-hand side, depending upon whether it's, row paired or column paired, such that you can reduce the LDE of the unitary strictly by 1. Now, recall earlier, reducing the LDE means sending our unitary step by step closer to the identity. So we are marching towards our destination of exact synthesis. Therefore, like this row paired and column paired reduction lemma can be thought of as the analog of the column reduction lemma that we mentioned earlier. So below, we're going to sketch the proof for the row pair reduction, and column pair is just a very similar idea, just up to the transpose of the matrix. Okay, so let's think of a U that is from L6. Oh, by the way, the reason I chose L6 is because L8 is too large for my slides and L4 is not interesting. So L6 is in between them. So if you're wondering, this is the reason. So let's say we have a column R1 to R6, and R1 corresponds to row 1, R2 corresponds to row 2, etc. Now, because we know U is row paired, right? It means up to permutation, we can put identical rows, meaning that rows that have the same parity on the same row, like on adjacent positions. Now, R1, R2 are adjacent, R3, R4 are adjacent, R5, R6 are adjacent. Now, they're of the same parity, meaning that if you perform this linear transformation instructed by the I tensor H, which is just blocks of Hadamard gate acting on the diagonal element, as you can see here, then we know even plus even give us even, odd plus odd give us even, odd minus odd give us even minus even give us even, right? This is just from the number theoretic knowledge. So we can derive, or like we can get a resulting vector, which is this guy, that is actually all even entries. Now we can factor out 2 from every component. So although, yes, when we are acting this I tensor Hadamard on this U, we bring 1 over root 2 scalar into this result, but because we're reducing the component by 2, like we're dividing 2 from both the numerator and the denominator. So in the end, we actually reduce the global LDE, or like this column LDE, by 1, as you can see here. Now, we don't really know what R1 prime to R6 prime is. We know that there are some integers, but they are just characterized by our this finite dictionary of binary patterns for our unitary group. And then this proves the lemma here. Do we have any questions up to this point? Okay, so, but what about when the binary pattern is not nice? Well, that's problematic because we can no longer apply this block of I tensor H to kind of, do even plus even or odd plus odd. But what we can do is we can conjugate this unnice pattern into a nice pattern. And then this conjugation is cost efficient, meaning that it only takes us 2 pairs of I tensor H, 1 pair of I tensor H. Then once we're again in this nice paradigm, we are dealing with a nice binary pattern, and then we go back to the previous lemma. So this is by direct computation. We're not getting into the details here. So in summary, if you have a element that is from the group L8, then what you can do is you can first factor out this 1 over square root 2 to the power of k, where k is the matrix LDE, and then look at its binary pattern. Now we can perform the synthesis by a induction on k. When k is 1 or 0, then it's a very simple case. You can just do either a sign flip or like a swap performed by this x alpha beta, and then, or you can just do I tensor H as we did before, do some linear transformation, and then you have identity. But if k is strictly larger than 1, then you just look at your binary pattern and say, oh, well, if this is nice, and if this is row paired, I apply I tensor H on the left-hand side, and I reduce the global LDE strictly by 1. If it is nice, but it's column paired, then I apply I tensor HP on the right-hand side. And know that here, this P is just a permutation matrix, kind of shuffle the rows and columns so that the adjacent rows or columns are, so that identical rows or columns are put in the adjacent places. Now, when the U bar is not nice, then you can just conjugate it as we did before. Okay, so as you can see, at every reduction step for from k to k minus 1, you are only using a constant number of the generators from the generating set F, right? So here, this I tensor H is an element and P is a permutation matrix. And this permutation matrix can be implemented by, this X alpha beta. So the cost is efficient and it only takes OK gate from this generating set. But now the problem is, okay, we know how to work with L8, but what about O8? When you do not have this scale of 1 over root 2 before your matrix, what happens? Well, this brings me to this method of using the commutation between the generators. So this is actually based on Julian, Peter, and my work that was published at QPL in 2021. So we find a set of complete relations for the group ONZ1 half. And this relation, I think there are only like 14 of them, is very efficient. And then the generators are also kind of using the same set. So it's very convenient for us to leverage the result. So what we observe is, well, we know that I tensor H is of order of 2. And we also know that if you push I tensor H through this 1 level, 2 level, and 3 level operators, you can get a new sequence of generators, but the cost is at most 3. Like, you will have at most 3 more generators than before. So the idea is, we know that we can think of an element of O8 as an element of L8, right? It's just like, instead of doing 1 over 2, it's 1 over root 2 squared. Now, we can first synthesize this element using L8 method, as we mentioned before, but then we have I tensor H. So what happens is, for example, if you have I tensor H on, kind of on non-adjacent positions, you can perform the relation that we just mentioned to push I tensor H all the way from left to the right, such that this I tensor H will be placed at adjacent positions here. Now, because this process of pushing is always giving you constant number of costs, and the number of push dependent upon the length of the generators, right? Because if you have 3 elements, k minus 1 and x, you're going to push it 3 times, first to here and then to here and then to here. So the complexity of such pushing is upper bounded by the length of the word in the notation here. So this is the reason behind it. So together we can combine the synthesis of L8 and the pushing that we just mentioned to define a global synthesis for O8 that only takes like OK gate to reduce or to kind of exactly characterize it. And this is described as here, which I actually just explained. And then you have the pushing and adjacent, and then you, oh, by the way, the other thing that you may be wondering is, oh, why do we know that I tensor H is definitely gonna be canceled out? Well, the reason is, if you are dealing with an element from O8, you know that your scalar must be 1 over 2 to the power of something, right? Now, suppose towards contradiction, you have an I tensor H somewhere in your word, but then this will bring you a factor of 1 over root 2. Then this does not fit into the group definition of O8, so this is a contradiction. Therefore, there cannot be oddly many of I tensor H in the word sequence that you derive, so they must be able to be canceled out at the end by this pushing operation. So this completes the proof. So in summary, our global synthesis algorithm has worked with this 1, 2, and 3 qubits, Toffoli-Hadamard and Toffoli-K gates circuit. But the problem is we have not compared it with the other state-of-art algorithm. The reason we need to do this is that we kind of are taking a shortcut, right? We are fixing the dimension, and we just, how to say this? Like, we're not really reasoning in a general sense, like we're reasoning for a very specific case. However, the nature of the global synthesis is that we are leveraging this unitary property on the global scale instead of the local scale. So we do not have this exponential buildup of the unitary when you're doing the column reduction. Therefore, we conjecture that when we're doing the benchmark, we'll have a really good performance compared to the AGR algorithm or the householder algorithm. So And we're currently doing it. Like we submit it to RC, and then we hope to incorporate our simulation result into the camera-ready version. And secondly, we want to define a standalone version for the global synthesis of 08, rather than relying on the corresponding result for LA and performing the pushing, because it's not very kind of implementation friendly if you want to kind of define the algorithm and then make it available to people using it. So if we have a standalone one, it's easier to use, and we don't really need to do the search and also the pushing. And we also want to extend the global synthesis to arbitrary dimensions. However, we do know that unitary synthesis is inherently hard, because when you have n number of qubits, the dimension of the unitary will grow exponentially large. This is inevitable. However, we are curious to see how far can we push the limit? How far do we have to absolutely stop when we're doing this dictionary construction? Like when we were doing the research, we tried to work with the 4-qubit Toffoli-Hadamard circuit, but it just got very, very large. The decision tree just expands in a dimension that, like, we are taking this how to say this, the enumeration of all possible cases, following the guidance of the technical lemma I just showed you. Then it turns out that there's just a lot of options. So maybe the best way to do it is to automate it using some programming languages. And then finally, we hope to just present the global synthesis results in terms of the circuit notation, then the M-level operators. And this is hopefully achievable by the end of April, because I'm implementing it now in Python. So, so that's the state of art. And finally, I want to thank you for your time, and I'm ready for questions.
Thank you.
Thank you.
Thank you.
So does anybody have any questions?
Yeah, I have a few.
Uh-huh.
So first question, I guess, you say your gate set is like Toffoli gates, but then you also talk about these like 2-level, 3-level, 4-level operators.
Yeah.
But like if I'm not mistaken, for say a 2-level operator, you need an n-controlled Toffoli, and the n-controlled Toffoli you can only construct without ancilla if you have the n-controlled Toffoli, because you can't construct an n-controlled Toffoli from just a regular Toffoli if you don't have at least one borrowed ancilla.
Yeah. That's very true. Yeah, like I believe we have read the same paper, so I know what you're talking about. Yes. So we are using a very loose notation because we did not mention how many ancilla we actually need. We think we need 1 dirty ancilla and 1 clean ancilla. This is actually the result of what you just mentioned about the multi-level Toffoli gate to represent this 2-level NOT gate. Like, yeah.
So other question then. So you have this special analysis for the 8-dimensional matrices, which correspond to 3-qubit matrices, I guess.
Yes.
So does this lead you to a better algorithm for general matrices? I didn't quite catch that. Like, can you bootstrap this to, say, work with 16-dimensional matrices where you sort of identify 8x8 blocks and you simplify those?
Right. The short answer is I'm not sure, but that's a very good idea. My worries is if you look at a column in a 16x16 binary matrix, it's very hard to reason just like locally by blocks, because there are some restrictions that we have to satisfy, right? Because it's of unit norm, it's orthogonal to other columns. So I'm not really sure how this local blocking would be helpful for applying the 3-qubit global synthesis to the 4-qubit global synthesis. However, so this year at QIP, I met Nathan Weep, and he's a professor working on blocking coding, and he mentioned something about like this blocking coding that only used like the local qubits. So what I'm thinking is, what if circuit synthesis is just inherently hard and there's no way that we're going to derive a general solution to it? But what we can instead argue is, well, can we leverage this small number of qubit synthesis to solve the Hamiltonian simulation in the blocking coding context? Like I'm still very new to this field, but I think there's something that we could explore there. Yeah, so that's the longer answer.
So the way you got to this better algorithm for the 8x8 matrices is, I guess, just brute force. Like you just identified 14 different cases just by sort of going through all the possibilities, and then
actually,
and then you have the nice ones, the not nice ones, the not nice ones. I guess you just try to see, oh, if I apply Hadamard before and after, does it simplify to the nice ones? So like this is probably not generalizable to higher dimensions because the number of cases probably blows up. Yeah,
exactly. So let me show you the. Oh, by the way, this paper is not on arXiv yet because we want to wait for the reviewers' feedback from RC. It's so but hopefully by the end of April. So so this is a decision tree that we built when we're doing this enumeration as you mentioned. And as you can see, we have many branches and we have many subcases, and every leaf give us a binary pattern from A all the way to this. And then we also have some not nice binary pattern, as you can see, this IJ, and like this. So I guess in one sense, we're very lucky, right? Because maybe when we're working with some other group, we may not get a finite decision tree. Yeah. Oh, and also if you want to look at how we do it, it's a very kind of naive. So we just start from filling in, okay, so we just do subcases, and then we start from filling the farthest that we can get. For example, like U5 is of, U5 means I think it's row, and then it's of Hamming weight 8, and then a column is of Hamming weight 8. Then following the lemma, which is the weight lemma, the odd entries must occur in quadruple, or the collision lemma, the identical entries must occur in pairs or evenly many times. Then we just fill it out. And then for the next case, which is the other direction, then we just filling another case like this.
Yeah.
So
and there's no way to do this in an automated manner. That say you have an algorithm and it's I give it like a really large matrix, and then it sort of automatically checks in which case I am, like if I'm in a nice case or not a nice case, and then it knows what to do. So without explicitly enumerating all the possibilities, like the algorithm would just know what to do in each case just by sort of algorithmically deciding. Would something like that be possible?
I think it's possible. Well, it depends on my computational powers, not depends on if my computer can deal with, let's say, 16 by 16 decision tree building and do this enumeration, then I guess it's possible. So, yeah.
Okay, and a final question. Do you know of a lower bound to the number of gates you need? Because we have an upper bound, I guess, but do we have a lower bound in terms of the least denominator exponent for how large the circuits have to be at least?
How large the circuit be at least? So do you mean the global synthesis or the local synthesis?
Just like I guess like you have a 2 to the n by 2 to the n matrix with a given denominator exponent. Then you then say, well, based on, let's say, a counting argument or something, like a general circuit for writing these down has to be at least this size, or like there have to be matrices that require at least as many gates to write down. Just because, well, if you have a 2 to the n unitary matrix of denominator exponent k, you can probably count how many different matrices there are of this size. And then given your gate set, you can see, well, if I have this many gates, there's this many different matrices I can write down. So probably you can derive a lower bound, like, oh, there must be matrices that require at least this many gates to write down.
Yes, I'm going to make a very, I'll make a very bold guess, but I think it will be at least okay. Because this is the number that is gonna always, there's no other way to reduce your matrix with LDE K, right? Like you basically, if the K is there, you literally just have to reduce it to 0. But I'm not.
Okay, but OK is a very lower bound, right? Like I would assume something like O n times K at least, or n squared times K, or like it probably has to have some dimensional dependence as well.
Right, that's a very good question. Hang on, let me think. So we're asking about the lower bound on the synthesis on any dimension.
Yeah. So if you look at the paper, some papers by Leah and me, we do this kind of analysis for a qubit synthesis where we show that like you need this many gates to write down an arbitrary permutation of a classical reversible gate, for instance.
Oh, I will definitely. Do you know which paper it is? I want to check it out and then maybe follow up a little.
Yeah, this is the Clifford+T synthesis papers, like that we can write down all the Clifford+T controlled Clifford+T gates using Clifford+T gates. Yeah.
Okay, thank you. Yeah, I never thought about this. Thanks for bringing this up, and I'll check it out.
Yeah, right.
Thank you.
Okay, does anybody else have any questions? I'm afraid I don't, because this topic is quite far out of my field of expertise.
It's okay. I also spoke very fast today, so if you guys missed it, I'm sorry.
No, that's okay. That's okay. I think it was the subject matter more than the talking. Okay, well, if there aren't any more questions, then thank you very much for speaking, and thanks everyone for coming. There won't be a talk next week because it's a holiday, a bank holiday in the UK, but there should be on the 17th, but I still need to work out a speaker for that. Okay, thank you very much.